When two solid metal plates collide, they don't naturally become one. Their atomic structures repel each other, maintaining a strict physical boundary. Yet almost every modern manufactured product is an assembly. From consumer electronics to industrial vehicles, engineers must force thousands of isolated components to cross that boundary and act as a single functional unit. Manufacturing has two primary branches: shaping parts and joining them. We are looking strictly at assembly and permanent joining. Here, engineers use three distinct paradigms to cross the physical boundary: mechanical fastening for physical interlocking, adhesion for chemical bonds, and cohesion for atomic fusion. Choosing between these three is a strict calculation, not a preference. The selection requires evaluating the physical limits of the necessary bond against the materials involved. Moving through this taxonomy requires shifting our perspective entirely, scaling all the way down from macroscopic components to the atomic lattice itself. The engineering choice made at this boundary dictates the final product's life cycle, its thermal integrity, and whether it can ever be repaired. At the macroscopic scale, we use mechanical fastening. This relies on physical geometry to interlock materials without chemically or atomically altering the base metals. Look at the structural geometry of these rivets. Whether they are solid, threaded, or blind, their unyielding shape allows them to pin separate plates together, creating extremely strong, lightweight frames. Because this is a purely physical grip, the internal metallurgical properties of the plates you are joining remain physically unchanged. This mechanism allows you to securely combine entirely different structural materials. A dense metal masonry nail can lock together with a molded plastic collar through pure friction and tension. The primary engineering utility of mechanical joins is serviceability. Threaded fasteners and pins allow a complex product to be safely disassembled, letting technicians replace parts that experience normal wear and tear. But there is a structural cost. To insert a mechanical fastener, you usually have to drill a hole. That hole immediately introduces a stress concentration point into the base material, creating a localized weakness. Mechanical fastening provides macroscopic structural unity, but it remains a physical compromise. The materials are pinned together, but they never truly unite. To eliminate those mechanical stress points, we step down to the microscopic scale. Physical adhesion bridges the gap by introducing a completely different chemical substance between the surfaces. Macroscopically, a metal plate appears perfectly smooth. Microscopically, that surface is a jagged landscape of microfissures and pores. Interfacial adhesion works because a fluid polymer flows deep into those microscopic valleys. Once hardened, it locks the surfaces into a solid block. This provides a distinct advantage. Adhesives can seamlessly bond dissimilar materials, like bonding carbon fiber to aluminum, which are physically impossible to weld together. Because the adhesive spreads the load across the entire surface area of the joint, you don't need to drill holes. The structural integrity of the base components remains intact, and because the application happens at room temperature, the base metals suffer zero thermal distortion. However, relying on microscopic pores means the preparation must be flawless. A single drop of oil or a layer of microscopic dust will prevent the polymer from gripping the metal. To achieve industrial strength, these high-performance adhesives require strict atmospheric controls and highly restrictive extended curing times. Adhesion offers material versatility and thermal safety at the steep cost of intensive preparation and vulnerable curing environments. When you cannot afford to wait for a cure and require maximum strength, you move to the atomic scale. Coalescence, or fusion, is the ultimate bond, turning separate plates into one continuous, monolithic piece. To achieve this, you introduce extreme energy to destabilize the metallic atomic lattice. Once fluid, the atoms from both separate plates merge and crystallize into a single structure. In industrial manufacturing, this looks like arc welding. The electric arc provides the immense thermal energy required to liquefy the metal. The AWS creates two main classifications: fusion processes, which use heat, and solid state, which uses pressure. Within fusion welding, the critical variable is the metal de aporte, the filler material added to the molten pool. If the filler matches the base pieces exactly, it's a homogeneous weld. Heterogeneous welding uses a different filler metal or joins distinct base metals. In autogenous welding, no filler is used. Extreme heat forces the base metal edges to fuse directly. While welding achieves true continuous monolithic strength, melting the material's atomic structure introduces a severe risk of thermal and mechanical distortion to the final product. These theoretical trade-offs dictate how engineers design production lines on the factory floor. In soldadura fuerte, or brazing, engineers utilize capillary action. A molten metal is rapidly drawn into a microscopic gap between two solid plates, pulling itself inward against gravity. Contrast that fluid dynamic with resistant spot welding. Here, sheets of metal are clamped tightly together, and a massive burst of electrical current is flashed through them. Instead of a continuous molten seam, spot welding isolates the extreme heat to small, evenly spaced circular bonds. The automotive sector relies on this because it provides rapid coalescence for thin metal sheets while minimizing the overall thermal distortion of the car's chassis. The engineering decision matrix maps these three joining paradigms against their inherent physical vulnerabilities. Achieving maximum atomic strength through welding inevitably introduces the highest risk of heat distortion. Securing maximum material compatibility using adhesives inherently demands extended, highly vulnerable curing times. There is no perfect joint. Engineering a manufacturing process is a strict calculation of compromises, deciding exactly which physical limit a product can afford